Have you posted the video from last Monday?
I'll do both of them tomorrow.
This week. Okay.
Yeah. The first 3 days of the week is very brutal for me because I'm teaching another course. Yeah. And the rest of the 2 days I'll at U of T, so I'm a mess this semester. Yeah, sure, thank you. Okay. So by last session we talked about linear regression, right? So, first of all, let's just have a recap on the learning notation that we talked about, and it was mainly focused around Hoeffding's inequality. So we talked about having a having two colored beans like red and green, so that they're in a big jar, and each of those have sort of probabilities if you want to extract those from the jar. And we talked about how we're going to distinguish these two, and we call them mu and nu. So nu was the in sample. Taking, for instance, we take 10 samples, our nu will be, in this case, we have 3 reds and 7 greens, right? And the rest that were already inside the big jar, so they're out of samples that we took. That's why we call them out of sample, or we show them by the notion of E out. And H was the hypothesis that was trying to sort of mimic the output of the real function f, which was the real probability of those two colors. And we expanded the Hoeffding's inequality using these two, and we thought the probability of having that bad news, which was the difference between your in-sample error and your out-of-sample error within a small margin of epsilon, is always determined, is less than equal to a negative exponential, and that exponential itself corresponds to your epsilon. So if you want to take epsilon smaller here, it's going to affect you in a negative way here, because it's going to diminish the effect of your n, and n was your sample size. So we thought that by having a very large n, chances are, and it's probable, possibly is probable, then these two are going to get close to each other. And we mentioned that this is going to set the foundation for our generalization theory, which we're going to learn, and that's going to be called VC dimension. All right, we started with regression. We thought, going back to the credit approval problem, so what we had for classification was when we have a feature vector of applicants, we call them x, starting from x0, which was the artificial coordinate, and x1 up to xt, which are the features you have starting from age up to the last one here. So when we have a label, which is an integer, so -1 and +1, we're going to have a classification, right? On the case of regression, that value of the label becomes a real value. So instead of having a label as to approve or reject, we're going to have an actual value, a real value of the credit line. Okay? So the output was a hypothesis x that is going to do a summation of all your values inside your vector w and your vector x, right? So starting from 0 up to d. And that was the vector notion of that. So we arrived to the point that, questions? We arrived to the point that how are we going to estimate our quality of prediction, right? So one of the methods that we brought on was to have a square error for each of the iteration of the training. So at each step, we have EI of W, the small e, and that's going to be simply the difference between your prediction and the actual output. So say your 250th iteration, you would have predicted this as 1500 as your credit card line, and the actual one was 1554. So you have to deduct this 2 and square it, and that's going to be your EI of W at iteration 250, right? And then when we sum them up and divide it, so we're going to have an average square error. We call it the capital EM of the W. Whenever we had the under bar here, or sometimes they use bar over that, so there are different notions. So we're going to have a vector. We're representing a vector. So this represents the whole vector of W, starting from W0 to WD, right? All right. Yep.
I'm just curious why we're looking for the average square loss. So every point will have its own error.
That's right.
So why do we want to find the average of all those errors? Like, does that, like, isn't each error unique? Why average it?
Because in linear regression, in a two-dimensional method, two-dimensional sort of feature, such as that. So say you have only one feature, okay, and that feature was cost. So X represents the cost here, cost, and Y was your sale, right? So that's your classifier. That's your linear regression line. We showed it by L, right? So that's your prediction. Each of the training examples you had in your capital X matrix are placed somewhere in this two-dimensional spectrum, right? So for each of them, you have sort of a difference between the actual value and your line that's going to predict, right? So in this case, we have 5, so we can produce 5 of E1 up to E, or starting from 0 perhaps to E4, right? So we have 5 values. In order to sum up the overall, we need to do the average square. We talked about some of the properties that average square is going to have a superiority over the absolute value, such as when we are dealing with different kind of variables, either they're independent or random, you can divide them as different components. So we talked about this. You can refer your previous slides. We talked about the expected value of two things. You can break them up. If you are using the square error, you can divide them into E of Y and E of X, and also the variance of those would be able to be factored this way. But if you use absolute value, these two are not equal. Okay, so that was one of the reasons we are using square error. Is that clear? Almost?
My question was just why the expected value? If every error is unique, why is saying this is the average loss of the function mean?
Because we are dealing with either an independent variable or a random variable, right? So, such as tossing a coin, right? Toss a coin, so in toss a coin, say you have 0 and 1, right? So if you carry on this experiment forever, the expected value of that is equal to half, right? Because chances are that after 2 million iteration, you have half of those as 0 and half of those as 1. So the expected value is a sum over that. It's half of them.
How well it predicts? Is that the idea?
No, we are trying to understand. Yeah, that's right. Yeah. We are trying to find a way to come up with a way to evaluate our prediction. Yeah, as sort of a loss function. Question? Yep.
Oh, so we're getting the average squared error, right? So how is this the same as the mean squared error, the MSE? Or is that just...
in machine learning, we have many different notation for the same formula. So in each context, perhaps in one context, it would be the same.
Oh, okay.
Yeah.
Okay.
Yeah. Okay, so now let's have an example about linear regression. So now we are interested in finding the relation between our advertising cost in 1 week for a company and the sales in that specific week after the ads were aired, right? So we are accessing to the historical data. So all the data are in the matrix D, and in this case we have only one small d, which is our feature, right? And that feature is only cost. So if we spend more, are we going to have a better sale? And in what order? How are we going to relate these two? So now we are interested in finding a line, a regression. So that's a regression problem, because we are interested in the value, a real value for that. So let's see how we're going to do that. We have come up with this L here, and these are the historical data, right? So we are almost pretty close to what the actual data was. Now we need to fit a linear model such that it produces that line L for us. So the linear model becomes y equal to W0 plus W1x. All right? W0 was our bias term, or the threshold in other problems. So we can define it as the sales when x was 0, right? And W1, as you see, is going to increase in sale for unit increases in cost. So it's pretty intuitive now. So now, we can have a refined model defining 3x, x1, x2, and x3 in our matrix x underscore underbar. So different costs are coming into account. So we are taking into account different costs. TV ads, radio ads, so these are dollar amounts. Newspaper ads, or I don't know, online ads. Right? So using that linear model with our different x's, now we're going to have our y equal to W0 plus W1x1 up to W3x3, which was the last one, right? And we can sort of come up with the initial w's that we think they are most related, just like the prediction model for students' mark when we wanted to come up with, right? We were trying to come up with some w's to start with. We thought if he's sleeping more, if he has studied more, perhaps the w will become more positive, and so on and so forth. So here we can just come up with the largest wi as the most profitable xi corresponding to that. So if x2 x1 was the most profitable, we can say that the TV ads, was having the largest impact. And we can start with this, and then the model comes up, and after training, it's going to fix the w's for us. Okay? So that's just the problem setup of that specific case. Now we're going to learn how we're going to solve this. For now, we just know how we're going to, design a problem. All good? All right. Now let's have a more formalized way to design your problem. So to obtain a better and more concise notion, we're going to write the collection of data points as row of matrices. So the matrix X, which we can show it also as this, contains all the features we have, right? And each of those features can be also a vector of features. So they could have underbar themselves, and they're gonna be from 0 up to d, the size, right? So if we represent, what's the question, someone? Was it?
0 to t, so total t plus 1.
Yes, yeah. So, all right. So this way we can call this design matrix. We're just expanding those vectors, right? Now let's see how we're going to minimize the error in linear regression. So now we have to come up with a way to minimize the losses in each of those W's that we learned. Because except those W's, the rest are constant, right? W's are the impacting factor in a linear regression or classification. Is that clear for everyone why the rest of the formula is constant except those W's? Is it clear? Not convinced?
Sorry, what did you say again? Which is constant?
So those x's are constant when we design a problem, right? For instance, for this case, those add values are constant numbers, right? We don't have to change them. We don't have to learn anything out of those, right? What we're going to learn is the W corresponding to the line of the hypothesis. And a W in two-dimensional way is going to change the line in 2D. In 3D is going to be in three-dimensional, and in higher dimensions, there's no way to visualize it. But that's the way you need to focus. You can think about that problem as you need to just find W's, because W's are the variables. All right? So now, we are arriving to a linear system of equations. Right? We have y of I, which is the output label, which was the real value of the ith iteration for the ith training data, has W0 plus W1x I and 1 up to W dx I and d. Right? So if we expand this, so we're gonna arrive to many linear equations for which the rows are the number of experiments, right? We show them by n. And the columns are the number of variables you had. So it's starting from d 0 up to d, so you're gonna have d plus 1, right? So in real world problem, do you think this linear system is a square one? Is it a tall one, or is it a fat sort of matrix shape? Any thoughts? So do we have sort of a square shape for this d plus 1, and do we have a tall shape for this, or do we have a fat shape? So who said fat? Why?
Because we do have like multiple characterization variables, for example, age, weight, and etc. These are the variables. So we do have a lot of variables, but a limited number of equations.
So what are those rows actually? Can you tell me what are these rows? So what are those? So what are those experiments here?
What do you mean?
So what does that n stand for here? Can you tell me?
N number of equations.
Right. So each of those equations coming from, where do they come from?
Real world examples.
So they're real world examples, right? So if I'm asking on that credit approval case, a bank to provide some data for me, right? So they're not going to provide it for one customer, right? They might just release it for the whole year, and that whole year might have like 1 million customers in there, right? So that's just one example. Or if you're collecting data from one of your experiments, you want to run it at least, I don't know, 10, 20, 100, 1,000 times, right? Okay, so we see that in many of the real-world problems, normally that n is much, much, much larger than your d plus 1. I mean, it needs to be larger because it's going to benefit your learning, and we're going to come up to that on the reason why. You should be pretty unlucky if you found a data set that has more d's than n. You're going to be very limited because you're trying to learn too much, right, out of your current experiments. Say you have like 200 features and 3 experiments, right? In math and also in statistics, that linear system doesn't have unique results, unique answer as well. We're gonna come up to that as well. So let me just so everyone understood what's the relation between D and N in normal applications? All right. So now by having this for all the training data or the number of experiments, we have a two-dimensional matrix, and we're gonna arrive to two conditions, right? So now, if D plus 1 is way bigger than N, which was your case, right? And that solution is not a good solution in machine learning because you didn't need machine learning for that. You could have to solve it, and we call it a model is consistent. Otherwise, when you have many experiments, so N is way bigger than D, we don't have any exact solutions. Remember, perhaps in your high school, so you had like y to x plus 3y, and then you had another one, y1 and y2, 3x plus 15y. I'm sorry, x1 and x2. Let's just have it x1 and x2 here. x2, x1, x1, x2. Okay, and you were asked to find x1 and x2, right? You remember it was possible. You could just define one of the equations by the other and find first x1 and then add x1 in the second equation and find x2, right? You had two variables, two equations. But here we have like 3 variables, 10 variables, so 10 features, those D's, and 1,000, a million N's, right? So there is no exact solution. If there was an exact solution, we wouldn't need to learn. We had the results. We could have just come up with some math and a formula to just solve that linear system. All right. So now, how are we going to come up with the best solution we have? So we need to approximate what we can do. So we need to approximate the summation of that loss function we defined in the previous slide. So here, this is in a vector format again. So that's the square error, right? The summation of square error, and we have to minimize this. So if we have multiple data points, we have to minimize the distance between these two. These 5 actually. So find a way to tweak the line. I don't know, here, making it here, and it should be linear because it's a linear regression. We don't want to go for higher polynomial in this example. So now, when we arrive to a minimization problem, there are so many different things you can apply, and they are spanned from, I don't know, operation research, algebra, and some of them are in machine learning, and so on and so forth. So there are so many methods for solving a linear regression. You just have to Google it and see there are tons of materials out there. And in general, they call the umbrella of solutions least square solutions. So they call least squares as is the standard approach to regression problems to approximate the solution of LR, right? There are many methods. You can apply a Bayesian model. You can do map. There are analytical solutions, geometric solutions, and perhaps other solutions that I haven't heard of. So these are different ways you can solve this. In this course, we focus on 2 specific methods. First, analytical one and the geometrical one. And so we're going to arrive to that in a few slides. And the next session, we're going to start with some examples of those. Okay? So now let's formalize the least squares here. All right. So now we arrive at the point that we have a data matrix of capital X that has all those vector of x's from x1 up to xn, and all of them are in the n multiply d plus 1 dimension of R. You know why, right? Because if you have n, we have d plus 1, right? And all of them are in R, real world variables, right? So that's your data matrix. Your target Y, which contains all the labels, and in this case we have regression labels, so we call it with capital Y, contains all the small y's, y1 up to yn, and they are real valued numbers, and they are n, right? They should match what you have there, because that's going to be another column here. So that's n, and this is 1. So corresponding to your x, you're going to have a vector. We show it with capital W or W underbar, starting from W0 up to WD. There are also D plus 1. So our model, our prediction model, should come up with this Y hat. So that's the prediction. And as that Y hat is sort of an arithmetic function of your data matrix and your vector, right? In the ideal world, in the ideal case, we would have Y hat equal to Y, but that would give us the perfect prediction, like 100% accuracy. But now we need to find a way to minimize the differences between these two, Y hat and Y. Okay? All right, let's carry on. So, I also put the corresponding reading materials in your reference book. So, in order to express the error in your in-sample, right, in-sample error, so what we need to do is just do a vector operation and to find the norm of this vector, your actual labels minus your predicted labels, right? And this is equal, if you convert it from vector space to a scalar space, you're going to have a summation of all those square errors, okay? So up to now, we knew everything from before. Now let's see, for finding the perfect in-sample error of W, there should be a corresponding W star for that. And this W star is our optimal solution for that. So we call it a star because that has the lowest error, right? Lowest. There could be many W's, but the one that has the lowest one, since we are interested in minimizing that function, we're going to call it W star. So we are trying to find that W star using one of the least squares method. All right, now let's just plug them all together and define a formalized minimization problem in the next slide. I've also uploaded these slides like a few hours ago. It's already in Moodle, so yeah. All right. So now, how to show them minimization error? So we are interested in finding a W star which corresponds to the arg mean of your in-sample error of the vector W. So that arg mean is just a way to showcase that this is a minimization problem given that domain, which is all your W's are coming from a D plus 1 dimensional space of R, right? So we need to find a W star that has the minimized E of n. And that's equal in vector space to finding the norm of that vector, y minus xw, right? So let's call that output f of w, right? And then we're going to talk about these two different methods to find that f of w, right? So, question? Yeah. There was a question somewhere? Yeah. Yeah. All right. So let's talk about the first method, which is the analytic method. We're going to arrive to this matrix, and it has a very simple proof. So we're going to present it in a few slides. So the analytical solution for minimizing the least square is through computing this matrix. So the W of least square can be computed by multiplying this matrix to your y, to your labels, right? So let's have a name for this. We call this a pseudo-inverse matrix of X, right? All those X transpose multiply X, all inverted, multiplied by X transpose. So we call it pseudo-inverse, and normally in statistics they show that with a dagger, X dagger. Actually, that dagger is a bloody one now. Yeah. So we call this X dagger, and that represents the pseudo-inverse. Sometimes there are dashes here. Sometimes it's just one word. So let's see what actually a pseudo-inverse matrix is that we need to compute in order to find a W, which was the solution of your regression problem, right? All right. We talked about this, that we have many n's, and also we could have many d's. In a case that n is way, way bigger than d, so you're going to have a tall matrix of X, right? That n is very tall, and you have d plus 1 here, right? So let's see what are the properties of X dagger that we are interested in using it. In a few slides, you'll understand why, how we came up with that pseudo-inverse. But let's just for now focus on why we are interested in using pseudo-inverse. Okay? So some of the properties are as follows. If you multiply X dagger, so the matrix of pseudo-inverse, to the matrix of X itself, you're going to arrive with I of X. We call I identity matrix, right? Let me just refresh your memory. So an identity matrix of I has 1s in diagonal and 0 elsewhere, right? And depending on the size, you're going to arrive to that specific size. So I'm just going to call it X. So 3, 4, 10. So that's one of the properties. The second one, if and only if the X dagger exists, so that's important, then for every matrix it's going to be unique. So we're going to have only one. The other one, which is very important for us, if X is invertible, right? If we can sort of, and do you know what the condition of being able to invert a matrix?
Set element should not be zero. That element should not be zero.
More general one.
Is that the x equals x inverse?
No, I mean, what's the condition that we can say X is invertible?
Say the word set.
What is it?
Should be a square mean.
Yeah, should be a square, right? So the reason X dagger has a superiority than the X invert or X minus 1 is that it supports it exists for every matrix. While on the other hand, the invert of a matrix is only exists for those that can be inverted, right? Okay, the property here is if X was invertible, that X dagger will be the same as your X inverse. But for those cases that the X was not invertible, you still have an X dagger. And this is a very good point for us because as we talked about here, chances are we are not dealing with a square matrix, right?
Also, that's the difference between square matrix and x dagger. This one can handle non-square.
Yes, X dagger can handle non-square matrix, right? While if it was invertible, that X dagger would be the same as your inverse. Yeah. All right. Another property is if you dagger X dagger, you're going to return to X. And I mentioned handle non-square matrices. All right. Now we see some of the interesting properties. I'm sure that there are thousands of those. You can just find it perhaps in that ebook that I uploaded on Moodle, or just Google it. Perhaps there are more to that. But the thing that is interesting for us is it's going to handle non-square matrices, and then the multiplication of X dagger and X is going to be an identity matrix. All right. Questions? All right, let's define another thing. Did you have operation research as a selective course? Okay. Have you heard of convex functions? How many of you have heard of a convex function? Okay. Could have been worse. No, I'm just gonna explain right now. All right, let's have another definition for us. So what is a convex function? So we call a function convex if the line segment between any 2 points on the graph lies either in or on or above the graph. Let's see what that means. Say you have this function, right? It's a function f. I'm going to pick 2 random points. If I connect these 2 points, the line lies on or above the graph. So that's a convex function. How about this? Is it a convex function?
Yes.
Do we have no's? Yeah. So yeah. Yes, have it. So if you pick 2 points here, it's gonna be inside. Is it a convex function? Why? So if I pick this point and this point, it's gonna be outside that, right? So likewise, this is not a convex function. It's gonna be outside, right? So having a convex property is very important in many operational research problems and optimizations. So we are assuming that we are dealing with convex function in linear regression here. right?
We are dealing with common function means that our y is kind of a common function.
That
The equation that we formed.
that unknown f that we don't know,
Yeah.
right? Yeah, we assume it as a convex function, right? Okay. All right. So let's have a look at some visualization. So we're talking about a special case that D is 1 now. So your W vector contains only W0 and W1, right? So your f of W, which was the solution of the least square we talked about, contains the W star, is equal to the norm of this, right? You already know that. So let's visualize it to see how we're going to minimize this. So now we have two W's and D was 1, right? So if we visualize this, we're going to end up with three axes. One for W1, one for W0, and one is that function, that f function, right? That's your W star. That's your W function, right? So now in 3D, you're going to have a shape, sort of a cylinder, but it's not quite like a cylinder. We call this paraboloid, okay? And in this paraboloid, if you see, this paraboloid is convex, right? I can pick any 2 points on the surface or inside, and when I connect these two, they're still inside or on the graph. So if you visualize it this way, that's your W star. So you have a function of f which is unknown, but you are interested in arriving to this point. And that point is the minimization of the error, right? Does that make sense? So each of the cubic sort of space that this represent has some error. You have to find a way to come up to arrive to that W star, which is on the lowest part, right? That's your W star. So starting from here, going that way, starting from here, going that way, or from the top, or from here, right? You have to find a way to minimize this. So that's the classic minimization problem. You want to minimize your function and find the optimal solution for that. That optimal solution here is W star.
So like this function this graph will create for every sample. Like
No, it's for all the samples. It's for all of them. Yeah.
so like,
Because now we are only representing W's
like,
here.
But for all the sample, y would change and x would change, right? If we
Yeah,
take all the samples, y would
That's
be
I got your point. So in this graph, those x's, those samples and lines are independent from what
and
you
we
see
are
here.
Taking that independent of y and x here, right?
Yeah.
So like it should be for like one sample in that case.
No, each of those samples will produce one of the W's here,
Yeah. So like
and you have to change this W0 and W0 was artificial. So here we can change W1 and arrive to a point that is W star, right? Because each of those tweaks is going to give you another error, right? So now if we slice it up this way, like the one that I dashed here. So say there was a slicer, I was slicing it up here. I slice it right this, and I look at it from the top, right? It's as if I'm lowering the dimension to the 2 dimension. That paraboloid becomes a contour. We call that a contour. And this plot that shows that contour is called a contour plot. So now we are looking at it from the top, right? And as you see, if it was a cylinder, we would have only one circle on the contour plot. But since it's a paraboloid, so it's starting from the top, it has the highest radius, and then you go down up to here, right? So if you slice it like this, you're gonna have different contours. If you look at them from the top, that's what you see over there. Okay? Does that make sense? So actually this represents your highest level, which was this, and this represents your lowest level, which was a W. Right? Because you had this, this, and this. Okay? So now, this contour plot, we have different level sets. So we call each of those lines that I just mentioned, we call it a level set. So as you see, these are constant here. W is constant, thus the minimization should be with respect to those smaller W's to find the W star. And W star is the one in the middle of those, which is that. This is it. Okay? I just wanted you guys to visualize what's your exploration space look like. Or in optimizations, they call this optimization space. So that's your space. There are many ways to come up with the optimal solution. One of them is using the Pseudo-inverse. Okay. Yep.
So each one of those, like, I guess layers, or like as you descend down it, those are like the different calculated errors for a given set of weights.
Yeah,
okay.
that's right.
This is the minimal weight.
Yeah,
set.
that's right. Later on, you're going to see in neural network that when you define and when you visualize the optimization space for iteration of a neural network, this squared there is an algorithm called backpropagation and gradient descent that resembles that descent here. So you start as if you're coming downhill and you want to descend to that optimal point. So how do you traverse this optimization space towards descending to the optimal solution which has the lowest error rate? That algorithm is called gradient descent. So we're going to talk about it when we start neural network. But for now, that's sort of a simplified problem in the case of linear regression. Yeah.
So in this diagram, so the y-axis represents the error, and the shape is a cylinder, right?
Yeah, it's paraboloid. Yeah, same. All right. So now we are interested in finding W. We are trying to come down to this W. So we are interested in minimizing f of W for all the W's in a d+1 dimension of R. Thus, in order to find that, we need to find the gradients. The gradients are those derivatives that you equal them to 0, right? I'm sure you know what gradients are from before. So we show the gradient by this upside down triangular. So this is the gradient of function f of W with respect to W. Because W was those that are the variables, the rest are constant. This is equal to this. Yeah, that's right, a partial derivative when you equal them to 0. So, let me just... Okay, so by equaling them to 0, I'm talking about a fat 0, which is a vector of 0, right? Because you're dealing with vector here. So all the partial derivatives, such as this, so d of f divided by d of W0, the partial derivative corresponding with respect to W0, up to derivative of f with respect to the derivative of W d is equal to 0. So this is the vector of 0, or a fat 0, right? So now we are interested in finding those gradients. All right, so let's go back to the proof of that pseudo-inverse we talked about. Our f of w is our square error, which was the norm of that two vector w vector and x w. If you expand this in vector space, this is equal to the same term y minus w x xw transpose multiply y minus xw, right? This is equal to the norm of this. Now we just have to do another expansion. So we multiply this to this to this, the second term to the first one, and the second term to the second term, and then we arrive up to here. So we have y transpose y, we have y transpose xw, minus we have xw transpose y, and then this one to this, xw transpose multiply xw, right? Let's simplify it a little bit. Now we arrive to y transpose y minus 2 of this term. We have 2 of that, and then we have a w transpose xt xw, right? This can be simplified. X transpose x can be simplified. It's an identity matrix, right? And then finally we arrive to this. So if I'm interested in finding the gradient of this function, it's as if I find a gradient for this value, right? That this is a gradient for all this value. Okay? Clear up to now? Okay, let's carry on. So in order to find that, we were interested in equaling them to the fat 0 matrix. So all of those terms should be 0. And as I mentioned here, this would be an identity matrix. So it's going to be 1 or I. So what you left with is minus 2xt y plus 2 x transpose x w, and then you bring the first term on the other side. You have this, and now if you sorted them out as for the term w, that w term becomes that pseudo-inverse matrix that you just saw. So in order to find the w, you need to actually compute the pseudo-inverse matrix and just multiply it by labels. So that's why you see least squares. Least square method in this case, the analytical way, or linear regression in general. Why this is such a simple problem to solve? Because if you take this approach, you're gonna just have to just compute the pseudo matrix and multiply it by y. You're gonna have your w in the linear case, right? So that's going to be a least square solution. Let's see how computationally intensive this method could be, right? Because we are dealing with so many matrices here. Let's see, is it hard to compute that or is it easy? Okay. So now, the solution for your w, the w least square, was your inverse matrix multiply your labels. So you remember that this one, X transpose was having a D plus 1 multiply N, right? Your X was the other way around, N multiply D plus 1. And you have to invert that. And that inverse, you think, oh, that's going to be very computationally intensive. But let's see if it is or if it isn't. Then you have to just multiply it by transpose X. Because in many problems, you arrive to with a matrix of, I don't know, 1,000,000 to 1,000,000, and then you have to inverse that. And then you need a GPU or you need a supercomputer for that. And then you're outside your memory range, and there are so many different things you have to apply. But let's see, using a pseudo-inverse in the problem that normally we have many n's than D, what's going to happen? So if you wait here, and then let's calculate what's inside. So what's going to happen inside here?
It's going to form a dividing matrix.
Yeah, you see that? Pretty interesting. These two are going to get resolved, right? So at the end, we're going to have a very, very small matrix of D-dimensional, D by D, or D plus plus, D plus 1 and D plus 1, right? So say you had 4 features and 1,000,000 experiment, right? 4 features and 1,000,000 experiment. Super tall matrix. If you weren't going to use a pseudo-inverse, you would have to spend a lot of time computing all those inverse of those 1,000,000 rows, right? But using this pseudo-inverse, you just have to compute a 4 by 1 here. And then inverse that. Then multiply it by D plus 1 n matrix of this, of the labels. So you see, least squares linear regression. In the case of linear, because we have quadratic as well. In the case of linear, this is a very simple problem to solve for computers, right? So like instantly you can have the results right in front of you. And people have come up with ideas that, okay, so if it's solving the problems this fast, why not we use it for classification as well? First of all, can we use regression for classification?
Yeah.
Why?
Because let's suppose we have in classification just 1 or 2. So like if we are getting if we're changing it to regression, we can have 1, 1.5 and 2, and we can use 1.5 as 1 or 2, whatever.
Right.
Program.
Yeah, that's right. So at the end of the day, your integers are also from R, right? They're human for themselves, right? You can treat them as R, the real value. So you can use regression for classification problem. Although you might end up with a prediction that is, instead of 1, it might be like 105, which in real world doesn't make sense. But you have to come up with some, I don't know, a flooring of that or ceiling of that to find the classes. But let's see if we can use linear regression for classification and then adopt your PLA or pocket algorithm on top of that. And that's exactly what's happening in many of the algorithms that are taking into account linear regression before using a classification. It's as if you are using it as the initial results for the classification. So let's just wrap it up here. Linear regression learns a real valued function, right? Those were those were in R. So the binary values are also real valued, of course. For instance, -1 and +1 also in R. So we can use linear regression to get an estimate, a close enough estimate of your, YNs. More certainly instantly, because that matrix is pretty easy to compute in modern computers. And then we can either leave it as it is if we were happy with the results, or we can start training using our previous classification methods that we knew, using PLA or pocket algorithm, right? Does that make sense so far? So say if you had these pluses and these minuses, and then you were to apply PLA, it would have a start perhaps here, and then it would find, oh, I have this misclassification here. Let me just tweak the line here on this side, and then I'll have another line here. I have another misclassification here, and then so on and so forth, right? So that was a classic PLA. Now, if I use linear regression, I might just end up with a line like this, right, instantly, to minimize the errors. And then using that, you can start as your initial weight for classification. In this case, you solved the problem already. In a case that the data was not linearly separable, just the previous example in the previous lecture, we had like some pluses here and minuses there. So linear regression might come up with a line like this, and then your pocket algorithm can just tweak it a little bit up and down and stop, right? So you're going to save a lot of iterations if you start from the result of a linear regression for your classification. All right. So let me just quickly discuss the second least square solution, and next Monday we're going to have examples of both cases. So remember, we were talking about the geometric interpretation of your least square solution. If you take a look at that minimization problem from the geometric perspective, you need to find the span vector of your matrix X. So what does the span vector mean? So we call a set of S vectors, or here we call it Q here, in a vector space, is a smaller linear subspace that contains the set. So here we have X, we have all the Q's, Q0, Q1 up to QD, and these are for each of the columns of your Q. So these are, think about it as a linear combination per column of your data, right? Yeah, Q is the ith column in X, so QD is the D column, Q1 is the I column. And we call this Q span matrix or span vectors of your matrix X, because you are able to represent your X with a linear combination using Qs. Okay? Geometrically, you can just think about it as projecting that to a hyperplane when it's 90 degrees. So that was your, given your observation vector, you can project that, and that's going to be your span. So those Qs are simply a set of linear combination of elements inside your matrix. So when we come back next week, I'll have an example for that. It's pretty easy to compute. And then we call this P, a set of all the span of X, right? Okay. So as if when we compute the pseudo-inverse, we are projecting the matrix on the hyperplane of your W matrix, right? So y hat is a projection of y onto the subspace P, and that's going to be the geometric interpretation of your least square solution. So we can sometimes call this H, and H is equal to that pseudo-inverse. So that H actually projects y onto the column span of X. So it presents a linear combination of your columns of your X, right? I provided another quick definition here. A set of vector spans a space if other vector in the space can be written as a linear combination. All right. For instance, you have A 1, 3, 2, 5. So you have two columns, 1, 3, and a second column, 2, 5. So if you want to find a span of that, the easiest way is just define two, based on the number of columns, define two variables, alpha and beta, and then solve that equation, right? So you're going to have alpha is equal to minus 5x plus 2y, and a second one is going to be 3x minus y, right? You find the alpha and beta. Thus, your matrix A can be represented this way. And 2 and 3 is going to be the span of M. So we call it the span M of the matrix A. Is that clear? That was pretty intuitive. Because you can define your previous matrix with a linear combination of another vector, which is actually as if you project that onto a hyperplane. We have more sophisticated examples in next week as well. So by now, you've understood what linear regression is, what these squares are, so different methods there are to solve that minimization problem. We are interested in finding the W star, which is the solution for the linear regression, or the least squares solution. We have one analytical method. We can use a pseudo-inverse to compute the W star, or we can use a geometrical method to find a span vector of that. And a formal definition for what you've seen by now is using for instance, the analytical method. We just have to construct the matrix of input, all those X, that design matrix that I mentioned, and your target output, so X1 up to Xn, compute the pseudo-inverse, X dagger, which was X transpose X inverse, multiply xt, and then return W as the X dagger multiply Y, right? Any questions? All right, so I'll see you next guys. I'll see you guys next week on Monday. Okay.